Okay students, so in this experiment we will be doing acoustic resonator, which will basically sort of simulate an atom, hydrogen atom. Okay. So what is this? There are two lobes here. Inside there is each lobe contains a hemisphere. So by joining them, you have inside there is a spherical cavity. Okay. So I will show you at the end of the experiment. So this spherical cavity there is a speaker here at the bottom, there is a microphone here at the top. Okay. So through the speaker you can put in sound signals using a function generator. So it will generate standing waves inside this sphere. Okay. Now these spherical standing waves that will be generated are analogous to the spherical harmonics of electrons in a hydrogen atom. Okay. So how they are similar, why they are similar, you have to look up the manual. Okay. So there it will be describing what is the analogous part, what is the non-analogous part. So only the spherical harmonics part of the hydrogen wave function we can consider it analogous to the sound waves. Okay. There is a radial part as well. If you remember, the hydrogen wave function has a r dependence, theta dependence, and phi dependence. Okay. So only theta and phi have a correlation with this sound waves in this pair. Okay. The r part is not. You cannot correlate that. Okay. They are not analogous. So we will only be looking at the spherical harmonics of hydrogen wave using the sound waves. Within that also, we will be looking at only those spherical harmonics. Again, if you have to go back to your basic quantum mechanics course, the spherical harmonics are given by this wave functions y, l, m. Right? You write L in the superscript, N in the subscript. So L represents the angular momentum quantum number, M represents the orientations of that angular momentum. Right? So here we can only sort of simulate m equal to 0 wave functions. Alright. So we will probably be able to look at y10 spherical harmonics, y20, y30, but not at y31, y32, those ones. Okay. Alright. So that is the basic part. Now what are the connections here? What are the connections? As I said, there is a speaker here at the bottom. Okay. And there is a microphone here. So where is the speaker? Getting the signal from? Again, this is a function generator. Okay. So what is its role? So using this generator, you can generate any kind of wave. Okay. A sine wave, trigonal wave, sawtooth wave, square waves. Okay. And you can control various aspects of those waves. Like what is the amplitude, what is the frequency. Okay. And then you can take that wave here and you are connecting it here. Okay. So this is the main controller for the quantum analog experiment. Okay, so this is called quantum analog because this is sound wave which are analogous to quantum phenomenon. Okay. Now here you are bringing it to this a T connector. This is called a T connector or a splitter. So here the sound waves are coming from the function generator and you are putting it in here. So sound waves output of the function generator is just electrical signals. Okay. The moment you feed this electrical signal to a speaker, it will create sound waves. So it is going into your controller and from there is a speaker output, it says, and there you are connecting the speaker. Okay. So this signal goes to the speaker. Also you see this signal, because there is a splitter, so this signal also going to the channel 1 of your oscilloscope. So channel 1 is the yellow trace. So whatever you are seeing here, this yellow trace is your sound input. You can say the sound input through the speaker that you are giving in the cavity. Okay. Or you can also say this is the output from the function generator. Okay. So this is the part that is giving you the sound waves here. Okay. Now there is a microphone which detects what kind of standing waves are produced. So you are putting in sound waves. So all the sound waves will not produce your standing waves. Right? So for example, if you remember standing waves along a string of length L. So only when your length L is an integral multiple of lambda by 2, only then you have standing waves. Similar restrictions also occur in case of a spherical cavity. So only certain frequencies will give standing waves. So whenever there is a standing wave, there is large amplitude, right, of the waves. Otherwise, the amplitude of the waves is very small. So that amplitude is picked up by this microphone. Once it picks up that signal, it sends this signal to the controller again. So you see, it goes in here. It says microphone input. That means it's the input for the controller, and it's the output for the microphone. Then it takes that signal and feeds into an amplifier. Okay, so this is a symbol for amplifier. And that amplifier, the output from the amplifier you are taking and putting into the channel 2 of the oscilloscope. Okay. So this green trace that you are seeing is basically your signal, basically amplified signal from your microphone. Okay. So whenever there is a standing wave, you will see a large amplitude here, and whenever there is no standing waves, you will see like a small trace here. Without the amplitude is very small here, if you can see. Okay. So you can also change the scale. That means the y-axis scale of the CRO by basically that means you are changing the calibration, right? So you are changing the number of divisions, the voltage per divisions. Okay. So you see, if I am making the voltage per division smaller, so my signal size is increasing. So I can clearly see that there is a sine wave as well coming from the microphone. Alright, so this is about the connections that you have to make here. Alright. So other than that, there is nothing else in the connection. So then I will describe briefly how to do this experiment. Okay. So as I said, so you will be creating standing waves here. So you have to first figure out what are the frequencies that is creating standing wave. Right? So what you have to do is basically do a sweep of frequencies. Okay. So if you look at the manual, it will say you can, for a start, you can do a sweep from 0 to 8 kilohertz. Okay. So as you sweep the frequencies, you have to keep your eye on the green trace. Okay. So this green trace will basically give you your microphone output. Okay. So if I look at my function generator, it is somewhere around 1.5 kilohertz at the moment. Basically, when you do the experiment, you will start at 0 or low values like 50 hertz or something like that. Okay. So I keep on increasing. So let's say I am at 1.5 kilohertz. I am tracing it. I have reached 1.5 kilohertz. And keep on changing it. Okay. Keep your eye on the green trace. You will see at some point it will increase. Now you see it's increasing. As I'm increasing the frequency, it's increasing. So using this knob, I'm basically changing the frequency of the output from the function generator. I'm not changing anything else. Okay. You see, you keep an eye on the unit trace also. Its frequency is changing, so it will become more continuous. Okay. But the amplitude is same. Okay. But the amplitude of my output signal is increasing. Okay. So I can also control by how much I increase in each step. Okay. There is a cursor here which probably you won't be able to see, but you can change the position of the cursor and you can control how much in each turn of this knob I am changing the frequency. Right now I am changing it by 0.1 kilohertz. Okay, that is 100 hertz. Okay, now I am at 1.6 kilohertz. So when you do the experiment, you will actually have to first reach the point near the resonance, and once you go there, then you have to increase the sensitivity. So you probably bring the cursor to a point like 1 hertz, like 10 hertz or 50 hertz, like that. Now it is at 100 hertz, right? So you can change slowly and figure out what is the exact resonance point. Okay, let me take a change now. So now it is at 1.6, still at 1.6. So now it's at 1.7. So you see it's increasing. 1.8, it is increasing. Also you see because the frequency is increasing, so this yellow curve and the green curve both are becoming condensed. Now you see it's, the amplitude is increasing, but the amplitude of the yellow one is not increasing, only the green one is increasing. You see, again you see now it has become quite large. Now you see it has gone outside the scale, so that means I have to change the scale of the y-axis for the channel 2, that is the green signal, so that it comes within my scale. So now you see it's within my scale. So this is more or less the resonance. Let me increase it further and let's see what happens. Now you see it dropping, right? Here it is very large. Again, if I increase further, it drops. So the knob is very sensitive, so one has to be very careful. So this is the resonance point. If I go a little bit lower, it decreases. If I go a little bit higher, it again decreases. Okay. So this is your resonance point. So in your actual experiment, you will change the sensitivity again and try to pinpoint the resonance point. Okay. So that is one resonance point. So you have to keep on sweeping at least till 8 kilohertz. Okay. And figure out what are the different resonant frequencies within this range from 0 to 8 kilohertz. Okay. So that is the first part of the experiment. So once you figure out what are the different resonance conditions, so each of these resonance conditions will basically represent one spherical harmonic. Okay. So different resonance condition is basically different spherical harmonics that you are generating. Okay. For example, if I start with the lowest one, it would be y00, yn equal to 0, n equal to 0. Then you have y10. Okay. Then you have y20, like that. Different spherical harmonics. Okay. In the second part of the experiment, we will do what? We will stay at one of the resonance conditions, any one, whatever you are figuring out. At one of the resonance conditions, we'll put the frequency there. So that means there is a spherical harmonic inside this one. Now we will try to see how the amplitude changes as I look at different angular positions. Okay. So remember, spherical harmonics is a function of theta and phi, right? So you have a wave function that is function of theta and phi. So as you change the angle, so its theta is changing. So you should get different amplitudes. So that we will do, and we will sort of make a plot out of it. Okay. So that we can, from this dependence on theta, predict which spherical harmonic this one is, right? So if you look carefully, this is the lower hemisphere, this is the upper hemisphere. In the lower hemisphere, there is a mark here. So, and the upper hemisphere is a scale. So we'll keep rotating the upper hemisphere so that the position of this microphone will change. Okay. And we'll have different angles here that we can read from here. And we will keep an eye on the amplitude. So what we will do as we change this angle, we will also measure the peak to peak amplitude. Okay. So basically, let's say from this point to this point. And as we change, we will also have to keep an eye whether this phase is changing. That means, now if I look at this graph at this particular position, this angle is called alpha. This alpha is equal to 180 degree. At this position, you see, if I just focus at this particular part of the curve, so this one is positive amplitude, this one is negative amplitude. It can happen that while you are rotating this part becomes positive and this part becomes negative. So that can also happen. So that means a phase change of 180 degree. So you have to look out for that as well. Okay. Otherwise, we will basically measure the peak to peak separation, count how many divisions are there, and multiply the scaling factor. That will give you the value in voltage, right? Okay. So now I'm changing the angle. You can keep your eye on the green trace over here. So you'll see that it is changing in size. So you see now I'm changing the angle. So it's decreasing in size, right? So as I keep on changing, you see it's decreasing, further it is decreasing. So it's very sensitive. So if I press it too much, it will change. If I touch it, make it a bit hot, it will change. So if you read the manual, it will say that don't keep touching this thing. Okay, see, if I am further changing the angle, it is reducing further. Okay. So this is the second part of the experiment. So once you do these two things, so you will at first you will basically sweep, and then the second part you will pinpoint at one of the resonant frequencies and see how the amplitude is changing with theta. Now this angle also is not directly theta of the spherical polar coordinates. You will have to read the manual to figure out what is the connection between this angle and the theta. Okay. Why is this not theta? Because this is giving me angle with respect to the z axis here. Okay. But the spherical harmonics are set up by this speaker here, right? So the axis of the speaker to the microphone is like a slanted line. It's not that z axis, right? So you connect the two things. Okay. So this is basically the part, the experimental part here. So now the experiment is over, so I just wanted to show you this two spheres. Okay. So you see there are like two hemispheres here with a cavity inside. Okay. So once you join them, it makes one full sphere. Right. So here you see there is a microphone inside, and then there is this BNC connector. Right. Similarly, if you look at the other lower hemisphere, you will see that this one has a speaker inside. So this is the speaker that is giving you the sound. Okay. You give the function generator, the electrical signal from the function generator is converted to sound by the speaker. Okay, so this is the experiment. So thank you for listening.